So last time we started looking at a new kind of integral called line integrals. And there's going to be three kinds that I will need you to be aware of and responsible for. And we started the first type, and it's called a scalar line integral. And the only application that's really relevant for a scalar line integral is mass of a wire. Okay. But we need it in order to segue to the two other kinds of line integrals, which we'll be using and are much more common, especially with physics. Okay, so just to recap, when you're doing a line integral, you're integrating over a line, but more specifically a curve. It could be 2D or 3D. The look of the line integral looks like this right here. Ooh, hang on a minute. I'm having some problems here. There we go. The two-dimensional version looks like that, where you're going to have a C underneath the integral symbol. That stands for curve. C stands for curve. And then you'll have a function here, and then ds, not dx. If I see you put dx there, problem. Because ds represents arc length element. And so when I did the quickie penumbra of a derivation here, when we were taking subintervals of the wire, we were taking little pieces of the wire along a certain length of the wire. And that's where the arc length element comes in. That little delta S sub I here turns into ds. And so it's really important that you get that little ds like that, arc length element. And you recall from way back when we did arc length when we were doing vector valued functions, and the arc length for a 2D is the speed, basically. That's the magnitude of the velocity. So you have to remember that. And so this is the formula that you need to know. That's going to be on the final. So this is kind of like good review for the final. You need to know your arc length formula. Now, when somebody gives you one of these weird weird line integrals, how do you integrate it? You don't just go, oh yeah, I can integrate that, because I can't do it either. You have to turn it into a regular single integral, calculus 1. And so to convert it to a regular integral, you're going to convert it to an integral where the variable of integration is t. Typically, t represents time. And so when you do that, the curve already has to be parameterized. So somebody has to give you, or you have to go get the parameterization of the curve. That means get the vector valued function and a range of time, a time interval on which the curve is being integrated over. And then once you have that, you can go get r prime, and that helps you get the arc length element. And then the range of time t will be the limits on your integral symbol. And then the x, y's, and z's that are in the integrand, all of those have to be replaced, because you don't want to see x, y, and z in your line integral. You only want to see the variable t. So you have to replace the x with the x component you steal off of your vector valued function, and the y's get replaced with a y component, z's with a z component. I did one example last time, and now we're going to do another one. So I'm going to be queuing it up here for letter B. Evaluate this line integral, x squared minus y plus 3z ds. Remember, this ds here is not dx. It's important that you get that. It is ds, and that is the arc length element. Like that. We talked about different elements so far in this class. For example, we've talked about area element and volume elements. So you should have some knowledge of an element. So arc length element is a new one. Okay, this is a little bit harder of a problem, because big problem, they did not give us the vector valued function associated with the curve that we're going to be integrating over. But good news, we know how to do this parameterization, because we did this like in week 2 of the class. It's just a straight line. They're calling it C, a curve, and they're giving you the 2 points that make up that line segment. So we need to parameterize the curve. That's step 1. Cannot do anything until you do that. So recall that the parametric equations for a line, which is what we studied in week 2, you're just going to get that and then put those parametric equations into your vector valued function. So if we call the first point P and the second point Q, remember the PQ, the direction vector for the line, you know, you're just going to go terminal minus initial, terminal minus initial, terminal minus initial. I get 1, 2, 1. Yeah, you guys know this. And then X, Y, and Z, if they just wanted the parametric equations, and you can choose either of those 2 points, I'll just choose the 0, 0, 0, and then you choose your direction vector, direction numbers, oops, and that gives you the coefficient for T, okay? Now, what you're going to do here is put all those parametric equations into vector value function, and there you go. The only thing we need to do now is give a range of time. From what seconds to what seconds does this line segment sketch out? Now, it should be pretty obvious. Does anybody want to take a quickie guess?
0 to 1.
0 to 1. I think that'll work. Because if we plug in 0, we get the point 0, 0, 0, which is indeed the starting point for the line segment. And when we plug in 1 second, we get 1, 2, 1, which is the ending point. So I think this will work. Good deal. So that means we can kind of keep going forward a little bit. I'm going to get the velocity vector. Well, how come? Well, because I need to go get speed. The magnitude of the velocity vector, because that's going to help me get the arc length element. Okay. So then we can take this line integral, which I don't know how to integrate it. I have no idea. And we convert it to a single integral we can integrate. So the limits are 0 to 1 seconds. And then we're going to have this ds get replaced with square root of 6 dt. And then the question is, I don't want to see x's, y's, and z's in here. That's not okay. I only want to see the variable t. So x squared needs to get replaced with something. What? Well, we're going to take the x component from our vector valued function here and substitute that in place of x. So t squared minus y, but y is 2t, so we'll substitute 2t in place of y, and then plus 3z, but z is t. So this is what we are integrating here, and this is an easy integral that any Calc 1 person could do. I'm going to just combine like terms before I integrate, just because it makes it look a little cleaner. So I'm really only integrating t squared plus t, and I'm going to pull the square root of 6 since it's a constant multiple in front, and then I'll have an antiderivative here going from 0 to 1. Okay, and then my final answer is 5 square root of 6 over 6. Now, typically, these scalar line integrals should end up being a positive result because they usually represent the mass of a wire, although I have seen some Briggs homework problems where the answer ends up being 0 after you do all the work, or negative number, which is just weird. All I can say is that's weird. Now, I do want to mention that the value of the line integral, which is 5 square root of 6 over 6, is not dependent on the parameterization of the curve. So if you parameterize it differently than me, and remember parameterizations aren't unique, don't worry. You'll still get the same answer. We'll still end up at the same destination. So I'll write that down just to be clear that that is the case. So the value of the line integral does not depend on the parameterization, which is good news. So as long as your parameterization is precise, I mean, it's got to be accurate to what your curve looks like. I've seen people where they parameterize it, they parameterize for a straight line. They go, oh, look, I got the starting and stopping points for the curve, so I must have parameterized it perfectly, right? Well, if it's a curve and not a straight line, like this one was an easy one, the curve, if you will, air quotes, is a line. But in the next few examples, we're going to see the curves are curvy. And so if you just parameterize these curves by just looking at the starting and stopping point, and you're really parameterizing for a straight line, your answer is not even going to be close. So you have to have your vector valued function honestly represent the curve that you're integrating over. Honestly, not just the starting and stopping points matching. Everything has to match. Okay, questions? All right, we're going to keep going. We still are waiting for a couple folks to show up. So this one is going to be kind of interesting. Let's just follow what they're saying the curve is, and we'll even graph it. You don't have to graph the curve if you don't want to when they're giving it to you, but sometimes it helps to visualize. So here is a line integral, and there are going to be two pieces of the curve, which means we're going to have to parameterize twice and split this line integral up into two separate integrals, and then we'll add the results. So notice they're telling you the curve C is the union of C1 and C2. Okay, C1 is the curve starting at the point 0, 0, and it goes to the point 1, 1. Careful, not along a straight line necessarily, but in this case it is. So the C1 is going to go straight shot. But then, and this is going to be the hard one to parameterize, C2 is the curve starting at 1, 1 and going back to 0, 0 along y equals x squared. So there's your C2. So we have to be really careful because if you could think of this as a wire that's kind of bent around, we're basically getting the mass of the wire where the density function is given by x. Okay, so I'm going to do this very slowly, but here's what I'm basically saying. My ultimate strategy is this line integral is going to have to be evaluated by two separate line integrals. The first one along the first curve, we'll get an answer. And then the second line integral along the second curve. And then we'll get another answer and we'll add the results. So I'll do this nice and slow. All right. Yes, you're going to have this kind of stuff going on. It's going to happen. So let's do C1. We got a lot of work to do because we need to parameterize the curve. Parameterize. So what does parameterize mean? It means give me an R of t that represents the curve, and then tell me what the range is for time t on that curve. You know, so the starting and stopping time that will correlate with the starting and stopping points of the curve. In this case, the curve is a straight line. So this one isn't too bad. I claim if you do the parametric equations of the line business, you'll get an easy just t. So we'll call this R1 of t, t. And that works for this straight line. The question is, what are the starting and stopping points for my time? What's the interval of time that will correlate going with that curve? Anybody want to guess?
0 to 1.
Yep, 0 to 1 again. Now we're going to go get R1 prime because we need that for the arc length element. And then we can immediately go ahead and get the speed here, square root of the sum of the squares. And that's just going to be square root of 2. Is it always a constant? No. But in this case, it is. And so it's nice. So the C1x ds becomes a regular integral evaluated between the limits of 0 and 1. X gets replaced with the x component of your vector valued function. That's just going to be t. That's convenient. And the arc length element gets replaced with square root of 2 dt. So this is pretty easy to integrate. You know, no problems here. You'll just have square root of 2, t squared over 2, evaluate between 0 and 1. I get square root of 2 over 2. Save this for later. Save it for later. It's not the final answer, but we'll add that to the other line integral. Okay, so now the hard part. We're going to work on C2. We got to parameterize. Here's what not to do. even though it is y equals x squared, and it's really tempting to do what I told you to do 2 months ago. Hey, if you have a function of x, just let x be t, and then y is equal to t squared, and you got it. Well, the problem is, how are you going to have it start at the 0.11 and end at the 0.00? And you're not allowed to have time moving backwards yet. I'll let you have time moving backwards on the two other kind of line integrals. The book doesn't, but I'm going to let you. Okay, why can't you have time moving backwards for scalar line integrals? Because then you'll end up with negative answers. And as I mentioned before, scalar line integrals correspond to mass, and you don't want to have negative mass. Okay, so you need your time to move forward. So what does that mean? How are we going to parameterize y equals x squared? Well, since the starting point is here at 1, 1, my idea here, and you'll see this is going to work out. And I have a different approach in my book. For those of you who did buy my book on Amazon, I go over relating t to your x and y coordinates, and you'll see. So I'm going to let x be 1 minus t. And why does that work? Well, look, if I start at t equals 0, and I plug it in 1 minus t, that does have x begin at 1. And then if I finish at t equals 1, just say, that'll be my stopping time. When I plug in a 1 second into this x component, I will end up with 0. So it's perfect. It starts at 1 and ends at 0 for the x coordinate, which is exactly how this curve is oriented here. You have to honor the orientation. It's going backwards. And then since y is equal to x squared, that's the equation, we'll just take the x and square it. There you go, y equals x squared. And so if we have time moving forward, starting at 0 seconds and ending at 1 second, that accurately corresponds to this red curve I have here. It starts at the 0.11 and finishes at the 0.00. So it works. Yay! So now we go ahead and get the velocity vector, okay, and then, oh boy, we're going to have to use the chain rule unless you want to multiply all that out. And let's see, the derivative of 1 minus t is -1. And I'm going to clean up this R2 prime a little bit. Let's see, -1. And, it's up to you how you want to clean it. I don't want to clean it too much. Believe it or not, I'm not going to distribute the 2 or the negative. I'm just going to keep it out in front as a factor in front. You'll see why in a moment. Okay. And then when we get the speed, that would be the magnitude of the velocity vector, we go ahead and square our components and then add. And so this is kind of a hot mess. It's like, oh man, this looks horrible. But let's just leave it. I'm not going to expand and multiply. Believe it or not, I'm going to just stop there. And now what do I need a new piece of paper. What else is new? Good Lord. Always something. So then this C2 xds becomes the single integral 0 to 1. X, remember, you're going to replace that with the x component of your vector valued function. So that gets replaced with 1 minus t. And then the ds is going to get replaced with that yucky radical 1 plus 4, 1 minus t, the quantity squared, dt. Now, is this even integrable? I mean, this looks awful. And I claim it will be integrable. We're going to use the power rule with some u substitution. Really? Yeah. It doesn't always happen where you get lucky where these line integrals work out with this horrible radical. But this one does. If you let u be the radicand, trust me, okay? Really? Okay. What's du? Well, using the chain rule, we're going to have 8, 1 minus t to the 1 times -1 dt. If I clean this up a little bit, it's -8 times the other factor, 1 minus t dt. Now, good news, though. Look, we have 1 minus t dt already in the integrand. Cool. So all we need is a -8. So if you just need a multiple, no problem. Put it in, provided you multiply the front with its reciprocal. So now if I am rewriting this in terms of u, we just have to integrate square root of u. And so we know this from our wonderful time in Calc 1. You guys are all Calc 1 grads, right? So you'll get -1/8, 2/3, u to the 3/2. And I'll do a little bit of reducing here. That'll be -1/12. And then I'm going to put my u back in, which is kind of gross, but okay. There it is. Oh boy. Yeah. And then we're going to evaluate this antiderivative between the limits of 0 and 1. Okay. I'll pull the 1/12 out. So when I put the 1 in there, substituting, 1 minus 1 is 0. So this is really just 1 to the 3/2, right? Which is 1. Minus, and then when we substitute in the lower limit, which is 0, like so, we're going to get, well, that's not too nice, but it's 5 to the 3/2. Okay, fine. So, and this is just 1 here. So, yeah, that's, you know, it's not a really nice number, but it's good enough for government work. Okay, now what? Final answer of this line integral, you're going to grab the result from your first integral, which is that number there, square root of 2/2, and you will add to that this -1/12, 1 minus 5 to the 3/2, and you're pretty much done. I'm going to just call it. That's the exact answer. I know it's pretty gross. If I use my graphing calculator and punch in what the approximate decimal result is, there's the approximate answer. Okay, 1.56. And that's good that we got a positive result, because typically scalar line integrals, it's nice to get positive results. So that's like, yay. Okay, so welcome back, and how'd we do? The final answer, if you were in your breakout room and you got, I did see somebody, team made it to the final answer. You should have gotten, I had 6 pi times the quantity 1 plus 18 pi squared over square root of 2. And I know that's a weird, you could distribute the 6 pi if you wanted to, that's fine. And if I give the approximate answer, 144.47, which is a positive result, thank goodness, because this is supposed to represent the mass of a string. Okay, so if you did it right, you basically said, hey, the mass of this wire can be found by evaluating a line integral, where you put the density function 1 plus z in the integral. But then how do you convert this to, you know, a regular integral, where the arc length element ds, remember, it's not dx, you're going to go, what is the magnitude of the velocity vector dt? So your r prime, and this is after you distribute the 1 over square root of 2 for your r, you'll get negative sine t all over square root of 2, and then cos t over square root of 2, and then 1 over square root of 2. There's your r prime. So then your magnitude of r prime, that's speed, would be the square root of the sum of the squares of the components of this velocity vector. And so when you square all of these components, you do, you know, square root of 2 is, when you square it, you get 2. So here I'm going to get sine squared all over 2 plus cos squared over 2 plus a half. Okay, but then if I add these two terms together, keeping in mind that sine squared plus cos squared is 1, I end up getting oops, the square root, not a, sorry, square root. I end up getting a half plus a half under the radical, but a half plus a half is 1. So square root of 1 is 1. Does that always happen? No, but it's like, wow. If it does, you're like, that's nice. Makes it easier for me. I don't have some weird radical in my integrand. So then continuing on, your mass is going to be, you know, you're just going to 1, and then you replace your 1 plus z. Instead of 1 plus z, you have to replace z with something. What?
T.
T over square root of 2.
Over square root of 2.
Yeah.
Yeah. It has to be the z component from your vector valued function. And then you have dt, and I believe the limits for time were 0 to 6 pi. That's where the 6 pi comes from. And then this is pretty easy to integrate. You're just going to get t plus 1 over square root of 2 times t squared over 2, and evaluating this from 0 to 6 pi will get you the final answer that we got. Okay? Any questions on this? Scalar line integrals. I gave you an easy one that was already parameterized for you. In other words, the vector value function was handed to you. Nice, nice. Is that always going to be the case? No. Like that previous problem, we had to do all the parameterization and get the vector valued functions ourselves. It was a little bit of a hassle.
I do have like one question, and it's mostly about like the 6 pi. Because of the half, wouldn't that, because you factored out the 6 pi, wouldn't it be just 18 pi then?
Let's see, are you saying I have a wrong answer here?
Well, I'm saying that like if you distributed the 6 pi, you would get 18, you would get like 36 pi cubed.
Okay. So you want me to distribute the 6 pi?
Like, well, no, because like I'm just a little confused of like where the extra pi came from.
Oh, sorry. Yeah, that's right. This pi shouldn't be here. Sorry, that shouldn't be squared. Thank you. Yeah, after I distribute it, I get it squared. Thank you. Yeah, so if I did distribute my 6 pi, then that pi would be squared. Thanks, Nathaniel. You're right.
You're welcome. Just got a little confused.
Yeah, so like if I do this right here, I'm going to have my 6 pi squared, and then I'll have down here 2 root 2. And so my final answer is 6 pi plus 36 pi squared over 2 square root of 2. Yeah. But 36 over 2 reduces to 18. Yeah, you're right. 6 pi plus 18 pi squared over square root of 2. I stand corrected. Woohoo! Thanks.
You're welcome.
Okay, I'm going to keep lecturing now. No more breakout rooms. I'm just going to roll it. We're going to do vector line integrals right now, which is a different kind of line integral. And so we're going to do a little bit of review of something we did 2 months ago. We're going to talk about work. Why? Well, the line integrals we're about to look at represent the amount of work done, but it's a special kind of work because it's the amount of work done on an object as it moves through some sort of vector field. The vector field could be a gravitational field, or it could be electrical, or what have you. So we are going to look at work. Now, I know that some of you may have already taken a physics class, and so you probably are familiar with some of the concept of work. But I find that a lot of people, when they take physics, they don't really learn it. They just learn enough to be dangerous and do some problems, but they have no idea what they're doing, which is kind of scary because if you have a teacher worth their salt, they'll probably figure it out. So what about work? This is a review. This is review right now. Recall the first chapter, work done by a constant force, which is very rare. It's very rare to get a constant force. If you're lucky, you get a constant force, but that's not the case. But if you were lucky enough, then work is just the force multiplied by the distance that the object moves. Okay, so if you've got a big piece of granite right here, and it starts here at point P, and somebody pulls it with a rope or something, and let's say it ends up over here, where this point is now Q, this distance between P and Q is the distance that the piece of granite moved. And if the force is constant and acting along the line of motion, again, that's rare also, then this is just going to end up being the magnitude of F times the distance, and the distance would be the magnitude of that PQ vector if you obtain the vector for PQ, okay? But this formula only works if F acts in the line of motion. Technology. And usually you're not that lucky. What do you mean? Let's do another picture. And we talked about this too when we did projections. So let's do the real deal. Let's say again you have a constant force, but let's say it's not acting in the line of motion. So here's your piece of granite. And let's say your force, your rope, let's say you're standing a little bit at an angle with the horizontal there, call it theta. And let's say you're still able to move the rock so it ends up over here, stopping at the Q point. So what is your work now? Well, it's going to be the projection of F onto the PQ vector. That's going to be the force that the rock feels, is that component that's acting in the line of motion, times the distance. But then if you recall something from way back when, do you guys remember that if you have a vector U and a vector V and there's an angle between, the dot product of U and V is equal to the cosine of the angle between them? Oops. Times the product of the magnitudes of the vectors. Do you guys recall this at all?
Yes.
Well, it's going to be on the final, so it's good to know. So, so what? Well, this projection here, if you do all the work, and we did that in a previous lecture, so go read about it. It ended up where this work done ended up being cos theta. This is the angle here that's making with the horizontal times your force vector times the distance, but that is the same as F dot with PQ, and this is the key. So now let's look at this. We're going to extend this concept of work, and we're going to look at work done on an object as it's moving in a vector field. So notice all these arrows here, and there's a whole bunch of arrows over here too. You got some vector field, and we already talked about what a vector field looks like. You can think of it as a collection of arrows, maybe velocity of water or whatever. So it's whooshing. And here your object, which could be some bug or something like that, is moving in your force field. But what's the work done on that object? And it turns out the force in the line of motion, you want to project your force vector onto the unit tangent vector, because that's a vector that's tangent to the curve, and it's going in the same motion as your curve. So that's what you want to get. So they're even talking about that there. So if you remember, projection of F onto T would look like a scalar times a vector. And so this would be the dot product of those guys. And then down here, you would have the magnitude of the unit tangent vector. But what is the magnitude of the unit tangent vector? It's a unit vector, so what's the magnitude?
1.
Yeah. So that's where they got the F dot TT, okay? Because they're just projecting the force onto the curve. So a colleague of mine had a kind of a neat idea is, what if this were a roller coaster ride like this? And you know how when you're done with the roller coaster ride, you kind of come to a stop. Let's say somebody was pulling the car that you're in for your roller coaster. Well, the way that you would make it move the most is if you were pulling in the same line of direction as the cart, and the rails and the wheels. But if you were pulling a little bit off, then you wouldn't be, really pulling the cart as well. So that's another way of thinking about this, which is kind of cool. Okay, so now let's talk about a small subarc of your curve, delta S sub I. And keep in mind, this is just a little piece of arc length. It's like a piece of arc length that you're talking about. Okay, your work is going to be your force times your distance. Okay, but then what? You're going to have some F at that point, X sub I, Y sub I, Z sub I. This is an arbitrary point. A dot product with the unit tangent vector evaluated at that same point. Okay, so this is your force. You're basically stealing it from here. And then you multiply that by distance, the little piece of arc length. Okay, so this point is on your ith subarc. And so what's going to happen, we're just doing a quick derivation here. The total work done is going to be an integral, and it's going to be a line integral. Ooh, okay. So it's going to be a line integral where you're going to take your force, x, y, z, and you're going to take the dot product of that with your unit tangent vector, and then multiply it by a little arc length. That's your arc length element. Now, if I rewrite this a little less bulky, where I just write f dot t, so it looks a little cleaner, which is standard for most calculus books, then we're going to use some of our knowledge from way back. What is this unit tangent vector? Remember, it was just the unitized velocity vector. Oh yeah, that's right. So let's just write that down. So I'm just replacing big T, and there's still a dot product in there. And then we're multiplying that by a little arc length element. But what the heck is the arc length element? It is the magnitude of the velocity vector dt. But do you see anything that cancels right now? This is the key, people. Anything cancels?
Magnitude.
Yeah, it's gone. Gone, 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 gone. What? It disappeared? Well, yeah, like magic, baby. It's called canceling. You know, that's just a factor of 1 now. Really? Now what? Well, now I'm going to change tune a little bit. Let me use a different notation and on the r prime. Another way to denote r prime is dr dt. There's a dot product there still. Times, and you still have this dt there. And if you think of dr dt as a fraction, the dt's cancel now. And all you're left with is this line integral where f is doing a dot product with dr. And I call this the FDR line integral. It has nothing to do with Franklin Delano Roosevelt, but it kind of looks like FDR. And this is your very first line integral of a vector field right here. So the definition is you got a continuous vector field. It's defined on a curve given by r of t. It's, you know, you have it parameterized r of t. If it's not parameterized, then you have to parameterize the curve. You may not, you may have a lot of work to do, and then go do the line integral. And you got to figure out your limits on your time. Then the line integral of f on c looks like this. This is the generic look to it. It's an integral symbol with the letter c below. That lets you know it's a line integral, FDR, f dot dr. Well, I don't know how to do that. Well, nobody does. But I do want to say that this came from taking the dot product of the force vector with the unit tangent vector multiplied by the arc length element. But how do you turn this into a regular integral we can do business with? Here's how you do it. You take the range of your time, a seconds to b seconds, and that has to be there, or you have to figure it out if you're doing the parameterization. Those become the limits on your integral. And then your f, you're going to do a dot product with r prime. So that's why you have to know about dot products. And we talked about dot products in like the second week of class. No, I think we did it in the first week of class. Yeah, now it's all coming together, people. You're going to feel like an Olympic athlete going for the gold here in chapter 17, where vector calculus. So the thing here is normally you would have x, y, z here because your vector field is a function of x, y, and z. But I don't want to see x's, y's, and z's in here. If I see it, you're going to get a lot of points taken away. Well, how come? Because the variable of integration is t. So I better only see the letter t in this lovely integral. Well, then what do you replace x and y and z with? You already know because you did a scalar line integral, and it's going to basically use the same idea. If your r of t is given, say, by x of t, y of t, z of t, then everywhere you see an x in your vector field, you'll replace with the first component of your vector valued function, and everywhere you see a y, substitute y of t, and everywhere you see a z, substitute z of t, and then you'll just have t. That'll be the only variable, and then take your dot product and integrate, and you're done. These are fun. You're going to love these. Yeah. What's the relevance? What does it have to do with the price of t? I just told you. I just did a picture up here, in case you forgot. It's right here. You're finding the amount of work done on an object by the vector field as the object moves through the vector field, whatever the vector field is. Maybe it's the whooshing jacuzzi water, or maybe it's some sort of electromagnetic field. Who the heck knows? Could be a lot of different stuff, but you're figuring out work done. All right, so let's do another line integral, but this time a vector line integral. So they're giving us a force field. No, I'm already doing Zoom. Thank you. Thank you. Let me out of here. So they're giving you the force field. Interesting. And you could graph that if you wanted to see what it looked like. And we're finding the work done on some little particle as it moves along a helix. And oh, good news, they gave you the vector valued function. Ah, lovely. They did the parameterization for us. Ah, thank you. Please God, I love that. Now here's what they didn't do that's kind of mean of them, but you have to be a smart rat and play the game. They're not giving you the time interval here like they should. Normally when you have a parameterization, they give you the R of t and the components, la, 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 and then they give you time. They didn't do that here. Well, then I can't do the problem. No, sure you can. You're going to use your noggin. They're giving you a starting point and they're giving you an ending point. Well, how's that helpful? What you could do is set cosine t equal to 1 and then solve for t and you get a starting point, and then do the same for sine t, set it equal to 0 and t equals 0, and they better all agree that it's the same starting point. But I want you to notice one of the components for this vector valued function is simply time itself. Is that always going to be the case? No. If it weren't, you'd have to solve these three equations simultaneously. So I hope it's obvious to you that t is going to be 0. And then if you look at the ending point, this time is going to be 3 pi. Oh, they basically handed it to us. That was very nice of us, nice of them. And my erase tool doesn't work right now, so I'm just going to go 3 pi. Okay. Now, for those of you who want to go, well, what does that curve look like? It is a 3D curve. And in 3D, I wouldn't expect you to graph anything, but it is kind of fun to graph. So I just want to show it to you. I'm going to use the parametric equation tool here in my. So what do I have here? So the first component for this vector valued function is cos t. And then the second component, no, I don't want to move anything here. What are we doing here? Is sine t. And then this last guy is just t. And then when I graph it, it's the 3D curve. Whoa. Oh, it's only showing me a small piece, which is not very fun. So let's pull this up. Let's change our parameters. Let's change time to -10 to +10. And then let's have X, Y, and Z be something other than -2 to +2. That's no fun. It's only going to show us a small portion. We want much more. It's much more fun. Okay, we could do 0 to 3 pi, but I just wanted to see more of this curve. Let's see if that gives us. There we go. And that's kind of neat. You can see it is a helix, and it's a beautiful curve. And so you're integrating over that curve. That's cool. Love it. Love these things. All right. Vector valued functions. Nice curves. Okay, back to work. Oh boy. So hopefully you got from this definition that you're going to be doing a dot product. Well, you're going to be taking the force field, which is given, and you'll substitute in place of x's, y's, and z's, the components of your vector valued function. But then you got to take a dot product with who? This dr is basically r prime. So you still got to go get r prime, whether you're doing one of those scalar line integrals that I had you guys do, or one of these vector line integrals. Well, it's pretty easy to find this r prime, okay? And so your work done is going to be the integral going from 0 to 3 pi of the dot product of two vectors, okay? So we already know that the r prime is -sine t cos t 1. The vector field, I don't want you don't write this down. Like, this is wrong. I don't want to see x's and y's in there. That's bad. The 1/4 I'm okay with. I mean, you can't really do anything with the 1/4. He's just a constant. But I don't like x's and y's. So what are you going to put in place of an x and in place of a y? Any ideas? What are we going to replace x with?
Cos t.
Mm-hmm. And then instead of y?
Sine t.
Mm-hmm. And don't integrate yet. You still first have to do that dot product. Then you integrate. Don't try to integrate this. That's silly. Do the dot product. then integrate. I see people try to do the reverse. I'm like, what are you doing? Are you nuts? Okay, so you're going to multiply the x components together, and we'll clean it up in a moment. And then you'll multiply the y components together. And then you'll multiply the z components together, and you'll get some big old mess. And then you'll integrate that. But I like to clean up the mess as much as possible, if I can. And it turns out this is 1/2 cos t sine t, because a negative times a negative is a positive. And here we have -1/2 cos t sine t. Oh my goodness, how lucky are we? Well, these add up to 0. And so I only have to integrate 1/4. Oh my goodness, that's an easy problem. And then you're just going to have 1/4 t, where t goes from 0 to 3 pi. And you'll have 3 pi/4. Okay, and there is the work done. And they didn't give us any units, so I don't know what the units. The units could be Newton meters or joules. Or it could be foot-pounds. You know, it depends on your system that you're using. They didn't give us any info, so just leave it. Now, work can be positive, negative, or 0. You're not limited to anything when you're getting the value of work done. So that's kind of good to know. Any questions so far? Okay, this page is brilliant. Okay, so let's do it. We're going to look at a couple of questions, and then we'll answer those questions, although there's the answer. What about orientation of your curve? Does it matter if it, you know, what direction it's moving? Yes, that will affect the outcome of your line integral. How about parameterization? If you parameterize differently from somebody else, would that affect your answer? No. As long as you have a legitimate parameterization, not something you just pulled out of the air and like, well, this kind of looks good. If it doesn't exactly match your curve, it's not good. Okay, so we're going to be given a vector field, and we're going to just work with a vector field for both of the problems, A and B, here on this page. So check out this first curve. Now, if you graph it, you can use your graphing calculator. Let me remind you that if it's a two-dimensional vector valued function, you can always go into parametric mode on your calculator and graph it. I mean, you don't have to, but they are asking, you know, and I don't assume you have a 3D grapher, but GeoGebra is really fun. And you can always go online and access GeoGebra. I think my lab math now has a GeoGebra tool also, but if you go into here, ooh, I'm in polar, sorry. I think we were doing polar last time we did this. So let's do parametric. And if you go here, and let's clear that out, let's go 4 minus t. And then the second parametric equation is 4t minus t squared. Okay, and then the time is going between 0 and 3 seconds. So they just want a piece of the curve. And remember, there is an orientation. So right before I hit graph, make sure your eyes are on the screen and notice what direction is it going. Whoa! And it looked like it was kind of moving to the left. So there is a little piece of the curve there, and that's the curve we're going to do a line integral on. Fun. Nice. Okay. So over here, it's going to start here at the 0.40. That's when time t equals 0. And it's going to end up over here. And you got to put an arrow here so everybody knows the direction. And it's going to end up at the 0.13 once time t equals 3 seconds. And it goes along this parabolic arc. So there's your curve C1. So r prime, because you know I'm going to need it, is -1, 4 minus 2t. Fine. So this line integral becomes the line integral going from 0 to 3 seconds. And you're going to take a dot product of the force field with the r prime vector, and then integrate with respect to t. Now, the force field is yx squared, but you're not going to put y and x squared in there. I only want to see the letter t. So the y will get replaced with the y component of the vector valued function, and they luckily parameterized it for us. Thank you. And then the x squared, ooh, we're going to take the 4 minus t and substitute that in place of x, but then we need to square that. Oh, bummer. Okay, that doesn't look fun. And then let's do the dot product. Okay, so you're going to take 4t minus t squared and multiply it with the other x component, -1, plus the quantity 4 minus t squared, oh dear Lord, times 4 minus 2t. This whole mess, dt, 0 to 3. Yuck. Okay, I'm tired already just looking at this. It's going to require a lot of work. You're going to have to, FOIL this out and then distribute and let's just say et cetera, et cetera. Now, folks, when you get something like this on a test, I'm okay with you whipping out your graphing calculator and using the FNINT on your graphing calculator. Now, some of the integrals, I don't let you do that. Like if it's a cool integral, like I think on your midterm, I had something, it was a triple integral where you had e to the negative rho cubed, and then you had rho squared sine phi d rho d phi d theta. And this one, oh no, I don't want you like here, like this one here, this e to the negative rho cubed rho squared with respect to rho, that was the exponential rule. What I wanted to see there was if you let u be negative rho cubed, du is -3 rho squared d rho. And ooh, I already have a rho squared d rho. Cool. So you can go ahead and use the integral of e to the u du is equal to e to the u. I wanted to see that. So I was testing some u sub stuff. But if you've got a huge, big old, ginormous polynomial and you've got to do all this multiplying it out and go ahead and whip out the calculator, okay? You've my permission. You can even say it. I got to use the calculator because I'm going to go nuts. That's good enough for me. I get 69 halves. Okay. All right, fine. Now, what about this other curve here? I don't know. They parameterized it for us, which is sweet. So if we go to our graphing calculator and we graph that guy instead, what do we get? We have t is the first parametric equation there, and then we've got 4t minus t squared. Yeah. And then go to your window because here time t minimum is 1 second and the t max is 4 seconds. Okay. And then let's graph it. Oh, now it looks exactly the same as the other guy, except I think it's going in the opposite direction. Did you catch that? Mm-hmm. So it starts here at the 0.13 and ends down here at the 0.40. Oh, okay. So, is the answer going to be any different? Well, let's see. Okay. Same vector field and everything. So if you get your r prime, because you're going to need to, this r2 prime is 4 minus 2t. Okay, so then this line integral, which is f dot dr, becomes this integral. The integral going from 1 to 4. You're going to take a dot product like this. 1 minus 4, 2t. And then your vector valued function, which was y comma x squared, you're going to substitute in place of y 4t minus t squared. You just steal that off of the original vector valued curve. And then x squared is going to be t squared. Okay? And do the dot product first. Don't try to integrate without doing your dot product. Okay, so you're going to have 4t minus t squared times 1 plus t squared times 4 minus 2t. And once again, I'm too lazy to go do this. This one's not bad. I mean, this one, you don't have a whole bunch of expanding and multiplying. It's actually doable. But I'll just say et cetera, et cetera. Okay. And I get -69 halves. Okay, so I hope you can tell that if your curve is oriented in the reverse direction, that will affect your final answer. It'll be the opposite in sign. Okay. Parameterization does not affect. Okay. And now it's time for a meme. Sorry, I love that. I can't get enough of it.
We discussed line integrals in Calc 1?
No, there's no line integrals in Calc 1. That's why this is a joke. You get this smarty pants who thinks he knows things and he's discussing stuff he has no business knowing.
Oh my God.
that reminds me of a story about, I think it was almost 10 years ago. I was erasing the board. This is when we were teaching face to face, that was, it seems like forever ago. And a student came in, he was not my student, and he started asking me, I think I was teaching a calculus class and I was erasing the board. I think it was a calculus 3 I was teaching. And he came in and he goes, can I ask you some questions? And I went, okay. And he goes, what are all the indeterminate forms? And I went, okay, well, in calculus 2, they go over some indeterminate forms like 0 over 0 and, 1 to the infinity. And he started espousing a whole bunch of indeterminate forms. And I said, are you in calculus 2 right now? He goes, no, I'm in pre-calc. And then I said, well, it might be good for you to just wait until you get to calculus 2 and then, go and study that then and just focus on your pre-calc. And then I got a nasty email that very night. And it turned out it was a fake email because this wasn't his real name. And he just said some nasty things to me, like, how dare you quash my dream? And you're supposed to be an encouraging kind of person. And you told me to wait to do. I was like, what? Where did this come from? I don't even know the guy. And then he started to do the same kind of rude behavior to a whole bunch of my colleagues. And luckily it wasn't me, but they ended up in the VP's office and it was horrible. Okay, I have a problem just for you that I cooked up. So I'm going to put you in my buddies again. And this is a problem not in your course reader. Well, let me see. Is it? No, maybe I do have it. Yeah, there it is. Yeah, this is it. This is it. You and a buddy do this one. I thought I didn't have it in there, but I did put it in there. Yay. Okay, I'll give you a hint. You got to do a line integral. Yeah, that's your hint. So why don't you go ahead? I'm going to put you in your breakout rooms again. Let me open them up again and go in there and do this line integral. And it's not hard. Don't forget to do the dot product before you integrate. Okay, go. So how did we do on this FDR line integral? Did everybody get 9/4, I hope?
Yeah.
Yes.
Oh,
Yep.
perfect.
Yep.
So if you didn't, just a quick look see. Hopefully you got at least the vector valued function for the derivative. That's a good start. And good news, they already parameterized the curve for you right there. So you're good to go. Time is going from 0 to 1 second. You're going to take a dot product of your vector field with your velocity vector. And x, y, x, z, y, yz. Oh my goodness. So you're going to go, the xy will be t squared. And then xz will be t2t. Oh, I didn't give myself enough room there. And then yz, I'm substituting t squared and then 2t for z. Okay, that's a big mess. Let me clean that up. That looks like t cubed, 2t cubed, and we're going to take that dot product with the other vector 1, 2t, and 2. So when I do the dot product, I'll have t cubed times 1 plus 2t, that's supposed to be squared, sorry. 2t, that's 2t squared. Oh, trying to go too fast. That's a bad. And then 2t, and then plus 2t cubed times 2. Everybody get this? But isn't this a bunch of t cubes? Yeah. I mean, you got t cubed plus 4t cubed plus another 4t cubed. A lot of t cubes. I'm just going to add them all together. So I have 9 of those t cubed terms, and then go ahead and integrate. So I get 9/4 t to the 4th, 0 to 1, and then there you go. Okay. So anybody have any questions before we're done? We just wrapped it up, and we'll keep going with line integrals next time, and we'll get into more fun stuff with line integrals and conservative vector fields. Okay, so that's our next topic on Friday. Okay, so I'll stop the recording.